So now let us talk about ferromagnetism. Now ferromagnetism actually now we have already studied that the reasons behind which the reasons for which we see magnetism in matter. After the advent of quantum physics, it was the quantum mechanical ideas could explain that the actually the compensated, I would say, the uncompensated magnetic dipoles were mainly responsible for producing magnetism in matter. Now, so what Einstein and Einstein and D has said that the ferromagnetism occurs because of the spin magnetic moment of electrons. Okay, so the definite conditions, under definite conditions, the spin moments of electrons become aligned parallel to one another even in the absence of external magnetic field. So ferromagnetic materials, they exhibit what? They exhibit spontaneous magnetization and a spontaneous magnetic moment even in the absence of applied field. So this diagram shows a crystal. If you remember, I had been talking of crystals. Ferromagnetism occurs in crystals. Crystals means you have unit cells where every corner of the unit cell has atoms. Okay, so the dipole moment of the atom under normal conditions are not oriented in one direction. Okay, but once ferromagnetism sets in, you see all the dipole moments, they point in one specific, they all point in one specific direction. Okay, that means now they are aligned, and if you take the picture, overall picture inside the material, it looks like this. Okay, so Weiss, actually P. Weiss, he proposed a molecular field theory. So it was the molecular field theory, which was proposed by P. Weiss. Okay, so P. Weiss, around 1907, I believe, he proposed this molecular field theory to explain qualitatively the salient features of ferromagnetism. These salient features of ferromagnetism we have already discussed, and P. Weiss wanted to explain qualitatively the salient features. He postulated, what was his postulate? That the internal molecular field sets up spontaneous magnetization, and that a macroscopic ferromagnetic specimen is divided up into small regions which we call domains. So he was the one who proposed a theory called domain theory, propounded of domain theory. So he said that the macroscopic ferromagnetic specimen is divided into small regions which we call domain, and each domain is at all times spontaneously magnetized to saturation and has a definite magnetic moment. In a non-magnetized specimen, the direction of the magnetic moments of the domain are distributed randomly, as I have shown you over here, so that the material as a whole has zero magnetization. I showed you just now how it is distributed randomly. So the material as a whole has zero magnetization. Now when we talk of say spontaneous magnetization, here when we talk of spontaneous magnetization, then Weiss, he actually postulated that in a ferromagnetic material, the internal molecular field is responsible for lining up the dipoles in the same direction. The internal molecular field is Hi. So I call this internal molecular field Hi. Hi is equal to H plus gamma m, where H is the applied field over here. H is the applied field. H is the applied field, and gamma m over here is actually a measure for the tendency of the environment to align a given dipole parallel to the magnetization already existing. Tendency of the environment to align a given dipole. So, tendency of the environment to align a given dipole parallel to the magnetization, parallel to existing magnetization, parallel to existing magnetization. Okay, so the factor gamma is the molecular field constant. Here I call gamma as the molecular field constant. Let gamma be the molecular field constant. Okay, so it is also known as Weiss constant. Now this equation explains the Curie-Weiss law and the occurrence of spontaneous magnetization by assuming that ferromagnetics are essentially paramagnetic materials having a large molecular field. So this is a very important point which you need to know, that ferromagnetics are, this is different, okay, don't mix up, are essentially paramagnetic materials having a very large molecular field, having a very large molecular field. Is that okay? All right. So the susceptibility, as we have already seen, for a paramagnetic material chi, we have obtained it as C by T minus theta. Okay. So, well, it is obvious. So this actually you can show that this is equal to C by T minus gamma C. Okay, now the thing is, so you see, now the thing is that from the measurements of the susceptibility, if we observe, uh, if we measure susceptibility as a function of temperature, the internal field constant can be calculated. What is that internal field constant? Well, that internal field constant, which actually gamma, which is found to be of the order of 10 to the power 7, 10 to the power 3. Okay, now this value is actually 1000 times larger than the value theoretically calculated using the assumption of internal field. Now, using the assumption of internal field and interaction of atomic dipoles, if you calculate it theoretically, then you will see the theoretical value is much less. The reason arises why? Because calculation has to be done using quantum mechanical phenomena. What is it? You have to take the concept of quantum mechanical exchange forces between the dipoles. Then the value comes close to the value that is observed. Now, the equation which we had written, what is that equation? That the internal field Hi is equal to H plus gamma m. This equation suggests non-vanishing magnetization for for t equal to theta. Because of this equation, here chi we have written as c by t minus theta. So for t equal to theta, this should be 0, isn't it? But because of this equation, well, one can show that for t equal to theta, even in the absence of magnetic field, so for t equal to theta, H equal to 0, well, we see some non-vanishing magnetization still present within the substance. For t equal to theta and H equal to 0, well, non-vanishing magnetization is obtained. Okay, all right. Now, what does it mean actually? It means that the magnetization at temperature T less than equal to theta is spontaneous. It means that, isn't it? Well, see, when H is equal to 0, the magnetic fields are subjected only to the molecular field gamma m. Magnetic field is subjected to the magnetic field is subjected to the molecular field. What is that field? Molecular field gamma m, isn't it? So beta, which is the Langevin variable, isn't it? L beta is the Langevin function. So beta is the Langevin variable. It is given by what? Mu m h by kt. So this then becomes, because h is equal to Hi is equal to H plus gamma m, and H is equal to 0. So what will you have? Mu m gamma m by kt, isn't it? You'll have this. So from here you have m equal to from here we have m equal to what? M equal to, suppose it is equal to kt by gamma mu m beta, isn't it? So this is one equation. The other equation that we know of m from paramagnetism, you can call this as equation A. Call this as equation A. Okay. The other equation for m, okay, which we obtain from paramagnetism is n mu m, okay, cot of hyperbolic beta minus 1 by beta. This is the other equation. This equation we'll call as B. Let us call this equation as B. Okay, now working with these two equations, let us draw some important conclusions about ferromagnetism.